So this is the additional science chemistry unit 2 higher tier from November 2012. Was used this year, 2016 for the mocks for the year 10s. This is why you're interested in it. So first question then, we're looking at compounds. It's asking us which ones are only ionic. So it's asking you about, do you know the properties of ionic? So ionic compounds generally have high melting and boiling points. They'll conduct as a solution, but they won't conduct as a solid, and obviously they've got to dissolve. So we're looking for high melting and boiling points in these here, and we're looking for something that hopefully dissolves and then will conduct the electricity. So things that match that criteria here, we've got sodium chloride, which is high, it's soluble and it conducts electricity, and then we've also got copper sulfate. There we go, which has got a high melting point. Boiling point, it decomposes, which means it breaks apart, but it still dissolves. It's got the high electrical conductivity. So from the options available, we know it's got to be option C, copper sulfate and sodium chloride. We know it can't be silicon oxide because silicon oxide does not dissolve, so it can't conduct the electricity. We know it can't be octane, for example, here, because it's got low melting and boiling points. So it does help if you narrow some of them down, and no, it's definitely not that option. Two of them produce a coloured flame. So we're looking at the metals here, so we could go for the copper sulfate, and it's the copper that gives us the blue-green colour, and the sodium chloride, which is the high melting and boiling point there. Sodium chloride gives you the yellow colour, so it's, as it says here, name of the compound and the colour it goes, name of the compound and the colour it goes. It's got to be the right one for each mark. Why has hexane got a low melting and boiling point? Well, hexane is simple covalent. Whilst there's a strong covalent bond there holding the molecule together, there's nothing holding the molecules to each other. There's only the equivalent in molecule terms of something similar to gravity, which is the weak intermolecular forces. That's kind of like the friction in between them. So there's very, very little forces, or there's weak forces between them. And then for your second mark, you'd have to say that that takes very small amount of energy to break those very weak bonds, to overcome them. So there's 1 mark for saying the weak forces, and then 1 mark for saying that you need just a small amount of energy to overcome that. Hexane and water are immiscible. Describe how they can be separated. The key word there is immiscible. When you think immiscible, you should be thinking about the lesson where you learn about separating funnels. So that'd be your first mark, saying that you'd use a separating funnel. And that is as simple as like a glass beaker with a tap on it, and you turn the tap, and the most dense liquid starts to pour out the bottom, and you turn the tap off once that one's come out to stop the other one flowing in after it. And that's pretty much exactly what it says here. Use a separating funnel, and then scroll down a bit so you can see it, and then the bottom layer comes out. However you want to say that, OWTTE. That's words of it, to the similar effect. For a dot and cross diagram for hydrogen chloride, you need to show just the outer electrons only, which makes things nice and easy. It's dots and crosses, just to show you where the electrons come from. So on one side you have hydrogen, which you'd have as a circle, maybe with a H in the middle, and there should be 1 electron on the outside of that, so either a dot or a cross. Let's say it's a cross, so we do hydrogen on the left hand side with a cross on it, and then on the right hand side we do chlorine. It's in group 7, so we'll have 7 electrons in its outer shell, so we'll have 7, and the most important thing is right in between the two you'd have a shared pair overlapping, so it looks something like this. Here's one I did earlier. So there's the hydrogen, and it's got the 1 circle because it's in group, it's got 1 electron in its outer shell that it can lose or share in this case. And then you've got chlorine, which is in group 7. It's got 7 electrons around the outside, so it's got 8 now that it's sharing a pair here in the middle, and it's got 2 here in its full orbital now that it's sharing a pair. As long as you're getting this idea about a shared pair of electrons in the middle, you can always score marks on these dot and cross diagrams. So always just try and get those in the middle, even if you're not sure about the numbers and can't get it to balance out. For question 2, alkali metals should be a nice friendly one for you. Physical properties is the falling point for people here. It says physical, so you can't tell me anything about any chemical reactions, like it's setting on fire or fizzing or bubbling or anything like that. It wants to know about any physical properties. So that can be soft, low melting point, low boiling point, easily cut, low density, malleable, solid at room temperature. But a lot of clever people make the mistake of writing a chemical property there. As a part 2, explain in terms of the electrons why it's in group 1. So it is in group 1 because it's got 1 electron in the outer shell. That's worth 2 marks, that statement. So saying that it's got 1 electron in the outer shell, or saying they've got the same number of electrons in the outer shell, that'll get you 1 of the marks, and saying it's how many there are is the other point. So 1 outer electron would count for 2 marks as well, because it's saying that there's 1 of them on the outside, and that's the same for all of them. Nice and easy. Potassium is added to the water, so you will remember that lithium went on first and that just fizzled around. Sodium went on second in the demonstration, and that melted and fizzed around. And then the third one was cooler because it's set on fire with a lilac pinky purple flame, fizzing around. So we get all these marks for fizzing, effervescing, which is posh for fizzing, bubbles, floating, moving, forms a ball or melts, sets on fire, gets smaller, explodes, sparks, all really good words for what you would see. And look, it says see in bold, so it's a description of what's there. For this one here, balanced equation for the reaction, you want to make sure that you've got the same number of elements on each side. So the correct answer is D. If you have a look, we've got 2 Ks there, and on the right hand side we've also got 2 Ks. On this side here we've got 2H2, 2 lots of 2 would be 4, and then we've got 2 more H's here, and then we've got 2 lots of the whole molecule here, which gives us 4 in total on the right hand side. So it's just about making sure that it balances out and work through them all and get rid of the wrong answers. And part C, increasing reactivity going down the group. This is specifically aimed at the most stable in the higher tier. So it's down to the size of the atoms. Lithium's the smallest at the top, going down and get bigger as it gets to potassium. So that'd be one of the points to say, increasing the size. As they get bigger, the electron that's on the outside is further away from the nucleus. The reason that matters is the electron is negative and the nucleus is positive. So it's kind of similar to magnets. When magnets are close together, they want to stick together, and as you get them further away from each other, it gets less sticky. So similar sort of thing here if you look at the mark scheme. A bigger atom means that there's more shells or shielding getting in the way, which means that the outer electron isn't held as strongly or is easier to remove. Question 3. All the elements that are metallic, the way you know this is there should be a zigzaggy line here, and you've got your non-metals over here, and all these over here are metals. So that's ABC. 2 elements that are most similar, so they'll be in the same group, put there by Mendeleev. So that'll be A and B in the same group. Groups are vertical, periods are horizontal. For part B, an atom of element B contains more protons than A. State how many protons there are. So you could look at the periodic table and find that and count them. Or you could just go on the knowledge that each row means that you've had another full outer shell. So A would have 8 more electrons. So that'd be 1, 2, 3, 4, 5, 6, 7, 8 places. So it'd have just 8 more because it's a full outer shell. Remember, in group 2, it'll have 2 electrons in the outer shell. So this one would be 2.2 for the electron configuration. That would be 2.8.2, 8 more. That's 2.8.8.2, so it's 8 more. So that pattern continues a little bit. For part C, an element of E has an atomic number of 10 and a mass of 22. How many electrons does it have? So this number here is the proton number, and this one is the mass number. So proton number are the positives. So if we have 10 positives, we must also have 10 negatives to balance that out. So we'd have 10 electrons. For this one here, 10% of the atoms are 22 and the other 90% are 20. The easiest way to say this, if you didn't get it on the test, is it's just finding a percentage. So you find out what 10% of 22 is from that first line. 10% of 22 is 2.2. And then you get the 90% of 20, so calculator comes in there, divide it by 10 and you get what 10% is, times it by 9, oh it's 18. So we've got 18 and we've got 2.2, and when you add them together, then you get our final relative atomic mass of 20.2, which is our 3 marks. For D, the element in below in the periodic table is used to fill filament light bulbs. Explain why it's suitable for this. Well, let's have a look at E first of all. What's the clue? Oh, look, it's a noble gas. As soon as you start getting questions saying a noble gas, then you need to be talking about the fact that it's unreactive. You can't just say it's unreactive because there's 2 marks available, so you've got to think, right, why do I need it to be unreactive? What would happen if it's not there? If it's not there, then the metal inside would get really, really hot and it would start reacting with the oxygen, and we don't want the filament to react with oxygen because then it will blow. So the 2 marks that we're looking for here would be something along the lines of it doesn't react from this first cluster of suggestions here. That's to stop it reacting with the filament. You can also go for the scientific explanation. Look here on the mark scheme, you can say why it doesn't react. It's got a full outer shell. That's a great one to have for the noble gases. Whenever you get a noble gas question, it's got a full outer shell, it won't be reacting. Right, and question 4. If you're lucky enough to be with me, you get to do this one with a magnesium reacting in a little crucible. It's a great one for showing the conservation of mass. Right, so looking at the kit here, you've got a piece of magnesium being heated up in a crucible. The reason the lid's on is so that it just doesn't burst into flame and start giving out all this smoke. The results there will be useful to us in a moment, so we'll come back and look at them. Why has the lid been raised from time to time during the investigation? Well, we're looking at forming magnesium oxide. Where's the oxygen come from? It's got to come from the air, so you've got to open up the lid so it can get some oxygen in. For B part 1, we're looking at plotting a point on the points on the graph accurately. When you do this one, you should get virtually a perfectly straight line, and there should be one that stands out. When you get that one that stands out, part 2 is asking, right, why is that not on my perfect line of best fit with an absolute straight line? Reason could be maybe for any reason why the reaction might not have gone to completion. So maybe the reaction hasn't finished, or so there's some magnesium left unreacted. Maybe you lifted the lid off and it set on fire and all the smoke came pouring out, so some of the molecules escaped into the air. Maybe there wasn't enough oxygen around to do it, as long as you're saying any particular reason why the reaction might not have finished. A balanced symbol equation, easiest to get off the mark scheme here. MgO is nice and easy. Mg2 plus and O2 minus will balance each other out, but oxygen comes as O2, which should be expected to know that oxygen is O2. It's an everyday simple formula. Because I've got 2 of those, it means I must have 2 MgOs to get the 2 O's, and then because I've got 2 MgOs, I must have 2 Mg at the start. If you find the balancing difficult, ask one of us to show you, but even without the balancing, just getting the left and the right hand side, you can get 2 of the 3 marks available. And this is where it gets to be a little bit more tricky. So get your thinking hat on and listen to how the maths goes. So for an empirical formula, we need to know the elements that are there. So we've got lead as 0.414 grams and oxygen as 0.064. The way I'd usually set this out is I usually write the symbol lead on the left and then oxygen on the right, then start writing what you know underneath it. Don't get any marks for that, but it just helps you. So over on the left I'd write 0.414 and on the right I'd put 0.064. Then you get your first mark for using these numbers here. So lead has got a weight of 207 and oxygen is 16. So to make this a fair comparison, we're going to divide the lead by 207, and if you look, 207 fits into that 414 perfectly because they're nice like that. And we're going to divide this side over here, the oxygen, by 16. So you're going to end up with numbers 0.02 and 0.04. So you get a mark over here for doing 0.414 divided by 207 and this one divided by 16, because that's the mass of the lead and that's the relative atomic mass of the lead, and that's the mass of the oxygen and that's the relative atomic mass of the oxygen. And that gives you a ratio of 0.002 to 0.004. So you can get a mark for just writing that, or you can get a mark for simplifying it as a 1 to 2 ratio. You should be able to look at that and see 0.002 will fit into 0.004 twice, or you can always divide by the smallest number. Smallest number out of those two is 0.002. So if you divide that by 0.002, you get 1, and if you get that one divided by 0.002, you get 2. So that tells me I've got twice as many of these things on the right, the oxygens, as the leads. So I'd have 1 Pb and I'd have 2 O2. That's the empirical formula. Question, lots of blank pages. Question 5, energy changes. Instantly looking at these and seeing temperatures, you should be thinking about endo and exothermic reactions and working out which is which. This question asks you to explain what the temperature readings show. There's your first mark, talking about temperature, about the type of heat change. So if we've started at 19 and gone to 15, we've gotten colder. That means that energy has been taken in. So what your first thing would say, temperature's decreased, 1 mark. So when the temperature's been taken in, it's endothermic as opposed to exothermic, which would give out heat. You can still get a mark for saying heat given out, exothermic, for some strange reason on this. If we look at the mark scheme, probably because you knew one of the key words there that linked to it, even though you did it wrong. For part B, we got an energy diagram for exothermic reactions. Now we've got to think about this. Exothermic reactions give out heat. So they start off with heat energy, a positive bank balance of heat energy. And when they're exothermic, they will give that away. And if this was a graph of your bank balance after it's been given away, here's a start. So the products will be a horizontal line over here to the right, showing the energy after it's been given away. It doesn't matter how far up or down it is, as long as it is below this line, and it also needs to be horizontal. It's not going to be a diagonal line, it's just going to be a steady amount of energy in the products. Part C. This is a bit of a weird one because it's one of those where you do just need to remember this. If you go into A level, they'll give you more information about why it is like this and you get to do the calculations. But you don't want to do that because it'll just take too long. This is a little nugget of information. Heat energy is required for breaking bonds, and heat energy is released from forming bonds. So you've got to look at D for the answer. Now, one of the ways you can think of this is imagine that the molecules are kind of like magnets, which they are kind of like that. When you get the magnets attracting each energy, it doesn't take any energy for that to happen. So when bonds are forming, they don't need the energy. Whereas pulling those magnets apart does require energy. So when you're breaking those bonds, heat energy is required to break those bonds. I don't know if that helps. Hopefully it does. So on to the 6th marker. People generally do really good at answering for the temperature on this one, and they do really shoddy about either talking about the rates of reaction or saying how the surface area changes. So the good bit, most people will turn around and say if you increase the temperature, the particles start moving faster. The best people will then say because those particles are moving faster, they're more likely to collide, and then your superstars will tell me that more collisions means it's a faster rate of reaction. And it is important to say that thing because it says here, explain how the rate of reaction changes. So I've got to mention the rate of reaction in the answers. I would probably put that as your first paragraph and then start a second paragraph talking about the size of the pieces. Now, this is the tricky bit, and this is where people go wrong. If I have a big piece, I have a small surface area, like a big lump of sugar. If I'm dissolving stuff in a cup of tea, to make it dissolve faster, I could grind it up, and then when I stir in the powder, it gets to dissolve faster, because it's got a bigger surface area. So what I've got to be is really specific. When I increase the surface area by making it a powder, that means there's more surface area available for reaction, which means the reaction goes faster because there's more collisions. And you've got to be specific like that. You've got to say when the temperature increases, this happens. Or you can say it the other way around. When I make the temperature smaller or lower, the particles move slower. So you get 1 or 2 marks if you just say a higher temperature is a higher rate. It's just a fact. It gets you a couple of marks though. Get one of the sections done to a good level by saying something like I said at the start. Higher temperature means faster particles, more collisions, so higher rate. Good amount of detail, but you're only talking about half the answer to the question, so you can get 3 or 4 marks. Top end does the same level of detail, but you get the surface area the right way round. You don't say that a bigger chunk has got a bigger surface area. It's the surface area to volume ratio that we're really looking at, so it is the total surface area. Question 6, last one. Well done for getting this far. So looking at this, if we want to do calcium nitrate and find the formula for it, calcium's got 2 pluses. Nitrates have got 1 minus. That means I will have twice as many nitrates as calciums. So I'm looking for something where nitrates are doubled. Now I can't faff around and change nitrate, it comes in NO3s. So what I need to do is put a bracket around the NO3 and say I've got that twice, which is option D. For part B, number of oxygen atoms here. So it's checking your bracket skills again. There's O4, which means there's 4 oxygens, and it's in the brackets with a 2 next to it. So you've got to double everything inside the brackets. So that's 2 lots of 4 oxygens, which is 8 in total. Part C should be answered quite nicely. It can be really, really simple just to write down the electronic structure. So when it says describe in terms of the electron transfer, you could just write out what they have first of all. So sodium's got 11. So that's 2 in the first orbital, 9 remaining. 8 in the next orbital, 1 remaining. So it's 281, or 1 electron in its outer shell. First point here. You could do the same for the sodium. Sulfur. 2 in the first orbital, which means there's 14 remaining. 8 in the next orbital, which means you've got 6 left. So there's 6 in the outer orbital. So we'd have 2, 8, 6, or 6 electrons in the outer shell. Once you've got that down, you can start thinking, what would I write next? So when I've got 281, I've got 1 electron in the outer shell, which means I've got 1 to give away. Look, there's another mark. Loses 1 per atom. And you can even write that forms sodium plus a sodium ion. And that's got you 4 of the marks. You've not even talked about the sulfur yet in that case. The same thing can go for the sulfur. So it's got 286. It's not going to lose any. It's got a space for 2, so it's actually going to gain electrons. That's 1 mark. And you can say it's 2 electrons per atom because it wants to get to 8. So 6, 7, 1 more, 8, another 1. That's going to be S2 minus. That means we're going to need to have 2 sodiums donating electrons to 1 sulfur because of the numbers. So each sodium is losing 1, but each sulfur needs 2. So we need sodium to donate twice, which means it's going to be Na2S. Now, it seems like a hard question, and yes, there's a lot of information there, but there's a bucket load of points where you can get the marks. And starting with the electron configuration is the easiest way to go. And then we lead on to our last one, which is about ionic structures. Nice and simple. Read the question and you get a clue even if you don't know what you're talking about here. It says, explain the difference in the ability of sodium chloride and molten chloride to conduct electricity. Well, if there's a difference, that tells me that one does and one doesn't. So if you don't know anything else, you can at least guess. And that's where you get 1 and 2 marks from. Okay, so sodium chloride does not conduct as a solid, does when molten. So you could guess that 50-50. And that's a third of the marks on this 6 marker at the end of your higher tier. There's always a way to go. So the explanations for it, why doesn't it conduct as a solid? Well, first things first, to be able to conduct, you need a charge, pluses and minuses, and you need them to be able to move. Just like electrons in a wire for a metal, they flow along it. We want some pluses and minuses able to move. Picture a solid that you've drawn in year 7 with all those little circles in a regular arrangement. Now, in an ionic solid, they've got charges. So that's one of our boxes ticked. We need charges for electricity. But can they move? Well, if it's a solid, they just sit there and vibrate and can't move anywhere. So it can't conduct because they're held in place. And that's what we're talking about here. Strong ionic bonds, strong forces of attraction between positives and negatives. They're closely packed together. They can't move. So we're trying to get as much of the terminology in from here as we can. One massively important point. We are talking about ionic bonding. Okay, so we can't be talking about molecules, can't be talking about atoms. Big clue here where it's talking about ionic substances, so we're talking about ions, we're talking about pluses and minuses. Look at the whole question so far, pluses and minuses, pluses and minuses. So you've got to use the word ion to get 6 marks on this. Right, second part of it, why does it conduct when it's a liquid? When you melt it, or when you dissolve it, those ions that were held in place as a solid don't have those bonds anymore, so they're able to move. So we've got charge, yes, tick, good, and we're able to move, excellent, which means that they can conduct electricity. So again, we're looking over on the right here, we're looking at heat energy, overcoming those strong ionic bonds, so the charged ions can move. So, 1 or 2 marks. Getting it right that it doesn't conduct as a solid, and it does when molten. 3 and 4 marks. A simple explanation, like it doesn't conduct as a solid because something can't move. And when I say something, you might be saying ions, which is good, or you might be saying particles or atoms, which is not as good. In 5 to 6 marks, you're talking about the strong ionic bonds in the solids. You're talking about not being able to conduct because they can't move, and we're talking about ions specifically. And we're talking about conductors and molten because the ions can move. If you look at that sentence there, right, if you put a capital letter and a full stop in it, that is what 6 marks looks like in the most concise way possible. You might be wondering what the grade boundaries look like for this one. So we're here, the chemistry, unit 2 higher. go across to here. So you need 52 out of 60 for an A star. If you got 45 to 51, then you're looking at an A. If you got 38 to 44, you got a B. If you got 31 to 37, you got a C. If you get 24 to 30, it's a D. And if you get 20 to 24, then you got an E. Anything below that would be an ungraded mark. So hopefully you can see what you can do. If you do need any help or if you've got any questions on any of this stuff, feel free to come along and see one of your teachers.